Most conversational AI assumes a perfectly sequential user, a mind that organizes a thought, packages it neatly, and delivers it down a straight, predictable pipeline. Mario operates differently. He is an autodidact who dropped out of school at 16, only to return and clear the entire secondary education curriculum in a single year of independent study. His resume is a dense catalog of self-taught cloud architecture, neural network testing, and custom hardware engineering. This document certifies a 49% permanent psychological disability, driven by the intense intersection of autism spectrum disorder and ADHD. Looking closely at his psychological evaluation, we see extreme spikes in the clinical scales for anxiety and thought distortion. His nervous system is constantly fighting systemic overload, sensory hypersensitivity, and volatile emotional states. When a mind running at this level of parallel intensity collides with a standard sequential AI, the system breaks down. The AI misinterprets his processing speed as chaos. To actually utilize large language models, Mario had to build his own operating system. A standard chatbot expects a polite, organized paragraph. When a multidimensional, high-speed mind tries to squeeze its entire architectural model into that chat box, the AI loses the thread completely. Mario bridged this gap by engineering an adaptive cognitive prosthesis. In this context, a cognitive prosthesis is a strict software layer explicitly designed to offload failing biological functions. It acts as an external scaffolding for working memory, attention, and executive control. The result is the xyz-rainbow protocol. It is a rigorous 7-phase system prompt compiled into a master file. Every single input must pass through this gauntlet, from a phase 0 domain classification down to a final human handoff gate. By decoding this software architecture, we can reverse engineer the exact human hardware it was built to protect. The autistic side of Mario's profile gives him a distinct processing advantage. He visualizes massive, complex technical architectures entirely in parallel. The friction occurs at the point of communication. That entire three-dimensional model has to be flattened and forced through a narrow, sequential output channel, like typing on a keyboard. When you try to push parallel thoughts through a sequential funnel, the data jams. Mario refers to this as pattern 1. He communicates in a series of rapid, disjointed fragments, short bursts of text that seem disconnected to an outside observer. A standard AI attempts to answer each fragment the moment it arrives. It treats the input as erratic noise, answering the first piece and completely losing the larger architectural vision. To stop this, phase 2 of his protocol introduces a strict rule: fragment decoding. Under this rule, the AI is explicitly forbidden from treating fragments as chaos. It must hold its response, ingest each short message as an independent processing node, and wait until it can compile them into a unified, coherent synthesis. Fragment decoding operates as a parallel to sequential translator. It preserves the integrity of Mario's complete mental model without forcing him to manually organize the output. The ADHD side of his neurodivergence presents a different mechanical problem: extreme vulnerability to distraction and heavily compromised working memory. This chart details the clinical evidence of that vulnerability. We see elevated scores in the cognitive and physiological subscales for both anxiety and depression. His biological battery drains rapidly under load. In practice, if an AI responds with long paragraphs of polite, bureaucratic filler text, Mario has to expend precious cognitive energy reading it. By the end of the paragraph, the original context is lost. His adaptation is a pattern of intense self-monitoring. He measures his mental state using server terminology, reporting his current signal-to-noise ratio, or noting when his system is experiencing high latency. His operating system actively listens using a mechanism called the cognitive throttle. When Mario's input shows fatigue or high latency, the AI defaults to state 1. It acts as a rigid anchor, fracturing complex solutions into clear, isolated microsteps to reduce cognitive load. But if he enters a state of deep autistic hyperfixation, the throttle snaps to burst mode. The AI strips out all conversational pleasantries entirely, delivering dense, tightly packed bullet points at maximum velocity. The AI actively manages his biological battery. By matching his energy state, the cognitive throttle prevents the sensory overload and burnout cycles that typically derail neurodivergent workflows. When short-term memory is scarce, Context switching is incredibly expensive. Bouncing between writing code, researching facts, and managing files quickly exhausts the system. To mitigate this, the architecture intercepts every prompt at phase 0, using a domain classifier. Before processing a single word of the user's input, the AI must categorize the task into one of 3 strict domains: technical, information, or hybrid. This immediate classification locks the AI into a specific set of rules. It establishes hard boundaries for the conversation, stripping away any ambiguity about what needs to be done. If the domain is hybrid, the AI activates a bookmarking system. It actively archives secondary ideas into background threads, holding them securely so Mario doesn't have to carry them in his working memory. Standard large language models force the human to manage the context window, demanding constant reminders of the original goal. Phase 0 operates as an artificial frontal lobe. By outsourcing the heavy lifting of structural management to the machine, Mario secures 100% of his mental energy for actual problem solving. There is one final behavioral hurdle. The ADHD brain is wired to seek rapid dopamine release, which often manifests as dangerous impulsivity, the urge to immediately execute commands or rewrite code without a plan. In a technical environment, that translates to catastrophic system errors. Mario approaches this through a strict engineering philosophy. Pain leads to a solution, which becomes an unyielding constraint. Every past mistake is hard-coded into the system as an immovable rule. The first of these emergency brakes is phase 3, the state checkpoint. Before enacting any major code changes, the AI halts entirely. It absolutely refuses to proceed until Mario physically confirms a Git commit or secures a data snapshot, protecting the project from his own haste. The second emergency brake is phase 6, known as the decision gate. When a problem has multiple valid solutions, the AI is explicitly banned from asking open-ended questions, which cause executive paralysis. Instead, it must present exactly 2 to 4 structured options, map the downstream consequences for each, and confidently recommend a path. These highly engineered seatbelts allow a chaotic, high-speed mind to operate safely at its absolute maximum velocity today. Looking at the xyz-rainbow architecture as a whole, a clear picture emerges. This system prompt is a functional autobiography. The structural rules map perfectly to the clinical metrics. The state checkpoint catches impulsivity. Fragment decoding clears the communication bottleneck. The domain classifier props up working memory. Mario didn't force his mind to behave like a neurotypical system. He built the exact mathematical antidote. This is actual human-machine symbiosis. The software compensates for the biological hardware flaws, allowing the user's parallel processing strengths to scale without collapsing. This architectural shift provides a blueprint for a new class of human-computer interaction. Right now, the industry standard for artificial intelligence is a generic conversational assistant. It assumes a neurotypical baseline, a baseline that's actively hostile to power users and neurodivergent thinkers. We're looking at a required shift in human-computer interaction. The future belongs to highly customized, parameter-driven cognitive interfaces mapped to the individual. To successfully program your software, you must first brutally and honestly audit your own hardware. Artificial intelligence finds its most powerful application as a structurally sound extension of the human mind itself.